So we've been talking about enthalpy, and we've begun to label some enthalpy changes with subscripts, like we talked about the enthalpy, the molar enthalpy of combustion for a previous reaction. So it's time to talk a little bit about what we mean by different types of enthalpy, like what is an enthalpy of combustion and what other types of enthalpy changes are there. So remember, for example, the combustion reaction that we've seen previously is sucrose if I combine it with the stoichiometric amount of oxygen, it turns into carbon dioxide and water. So that's an example of, a specific example of an enthalpy of combustion, specifically the enthalpy of combustion of sucrose. So in general, however, that would be, when we're talking about an enthalpy of combustion, that would be converting 1 mole of anything, let's say some reactant A. If we convert that only into carbon dioxide and H2O, and if there were any nitrogen atoms in this molecule, converting those into N2, the products when we combust something, that would be a more generic example of a combustion reaction. So there's other types of chemical reactions other than combustion. In general, any reaction that turns reactants into products, we can call a chemical reaction. The enthalpy change for that process, we can always call delta H of reaction. So any reaction that we can write down, we can label the delta H of that process with the label delta H of reaction. We saw another example for the coffee cup calorimeter where we dissolved magnesium sulfate in water to form ionic, aqueous magnesium ions and sulfate ions, or whatever those perhaps recombine to form in an aqueous solution. That, if we wanted to give it a name, we could just call it delta H of reaction. We could call it a delta H of solvation because we've taken this reactant and we've solvated it, we've dissolved it in some solvent. So if we have 1 mole of a substance, an electrolyte that dissolves into ions in aqueous solution, then we would call that process a solvation reaction, and we would label its enthalpy change an enthalpy of solvation. There's a few other very common types of reactions that we can consider. One of the most straightforward to understand, although it's not all that commonly used, is a delta H of atomization, so an atomization enthalpy. An example would be, let's say if I took a water molecule and I decompose it into atoms, so gaseous hydrogen and oxygen atoms. I break the molecule down into its constituent atoms. To make that reaction balance, I would need 2 hydrogen atoms for every 1 oxygen atom. In general, if I'm talking about a molar enthalpy of atomization, I'm taking 1 mole of whatever and breaking it all the way down into gaseous atoms, atoms in the gas phase. So that would be called an atomization energy. The main reason that's interesting is because it tells us something about the bond energies or the bond enthalpies in that process. The enthalpy it takes to break water down into gaseous hydrogen and oxygen atoms is exactly the energy it takes to break the bonds holding the hydrogens and the oxygens together. And there's one final type of enthalpy that's going to turn out to be extremely important, and that's an enthalpy of formation. The F here stands for formation, and that's probably one you've heard of before. You've looked up enthalpies of formation in a table, most likely. For a formation reaction, the delta H of formation is the enthalpy associated with any formation reaction. So rather than decomposing the compound into its atoms, or rather than solvating it in a solvent, or rather than combusting it with oxygen, a formation reaction, we're going to form a mole. Let's say again, if we're talking about water, the property, the compound we're interested in water, we're going to form water, and what we form it out of, rather than forming it out of atoms, that would just be the reverse of this atomization reaction. What we form it out of is pure elements but elements in their standard states. So hydrogen and oxygen don't exist under standard conditions as atomic hydrogen and atomic oxygen. At room temperature and pressure, they would instead exist as gaseous H2 molecules and gaseous O2 molecules. So if I form H2O out of elements in their standard states, in order to balance that reaction, I need 1 hydrogen and a half of an oxygen molecule. And notice I've had to balance it with fractional coefficients because I specifically want to form 1 mole of the substance I'm interested in out of pure elements. In their standard states, meaning the states they would have at typically 273 Kelvin and 1 atmosphere pressure. So elements in their standard states would be gaseous hydrogen and oxygen. The delta H, or the enthalpy change associated with forming 1 mole of water out of elements in their standard states, that would be called the molar enthalpy of formation. So I could continue this list for quite a long time. We can talk about more different types of chemical reactions, every one of which we could label with a different type of label on the molar enthalpy. But this is just a sampling of some of the more common ones we'll see. And in particular, we're going to get a lot of mileage out of thinking about enthalpies of formation. Two comments I'll make before we move on is that these subscripts don't apply necessarily just to enthalpies. I could be talking about internal energies of combustion or internal energies of formation, but enthalpy is the most common property that we'll talk about for the next little while. And also, I'll point out that while I've been calling these delta H's of combustion or enthalpies of combustion, enthalpies of formation, it's also very common to hear these referred to as heats of formation or heats of combustion or heats of solvation. And the reason that's true, of course, is we know that enthalpy change for a process is equal to the heat whenever the pressure is constant. So when the pressure is constant, heat and enthalpy are the same thing. Pressure is not always constant, but experimentally it's relatively common to have pressure being held constant. So heat and enthalpy are synonyms in that specific sense. So when someone says heat of solvation or heat of formation, what they really mean is enthalpy of solvation or enthalpy of formation. It's a slightly colloquially, slightly inexact way of describing it that sort of has that assumption of constant pressure built into it. But the more formal language would be the delta H, or the enthalpy of solvation, atomization, and formation. Okay, so with this terminology under our belt, the next thing we'll do is to talk about how to combine different types of enthalpies for different types of chemical reactions and see what we can learn about multiple reactions happening in combination with each other.